Hey, so that's sort of things we attempted. You can also, if you really want to, you notice that we didn't have any type of t-values or p-values or significance checks for those random effects, but we can get them via LMER test, which is a package which allows us to test the significance of those random effects. So sometimes people just want a p-value for whether this is significant or not. That basically tell you, is there a significant variance between the schools and how they do it. So you could do it via the model comparisons and then say this model is substantially better than the other model, but sometimes people just want the p-value and say there's a significant, there's a random slope or random intercept is significant. Yeah. In order to do that, we just use all LMRE test and then we use rand as the command, and we then we'll print a chi-square value for significance of that level. So we'll just say, is that level significant or not? Yeah. So just telling you whether that variation which you see, whether that matters or not. So you can do some diagnostics checks, and I can also show you how to do it in sjplot. Sjplot doesn't always play nice with some other packages, so that's why it's not in this presentation, but I'll show you in a bit. And mostly we care about whether residuals are normal and linear, and we're looking for straight lines here. And I used a different package, which is Dharma, and it does something really nice with, like, it simulates all your residuals and does all sorts of fancy schmancy type of things. But we can then see what it looks like. So we can simulate our residuals from our fitted model, and we do 250 simulations, and then we can compare that to the actual data, and then we can have some type of thing. So we're looking for straight lines, and this is good. Yeah, you remember from QQ plots, if we get like significant deviations, things are going wrong with our residuals, but this is really as we would want it to be. And also in this one, we don't want to see straight lines. There's some type of angle to it, but normally you should see straight lines here, here, and here. There's some type of angle to it, but there's no systematic patterns going on there. So it's not a U shape or some type of funnel shape or something oddly going around. So these lines are just preference for your reference to help you. And if it's a perfect model, then you should have like straight lines at 0.25, 0.5, and 0.75. So you have some tilts, but it's not like there's, I don't see any really significant pattern in this, so that's good for us. Yeah, so you could sort of check what's going on with your models. We can also, again, we can do a formal test as to whether they're normally distributed, and we can test uniformity via Kolmogorov. So remember that you can test normality via Kolmogorov-Smirnov tests, and this just runs it, and we want that test not to be significant. So if it is significant, it means that our residuals are not normally distributed. Yeah, so that's a formal test if you want a p-value attached to it. But most of the time, it would be sufficient to check graphically. So if you see this type of pattern, it would mean it's all good, nothing is going on. Again, think of the residuals as your trash bag of your analysis. If you build a perfect model, there should be no patterns in your trash bag. If there are issues, you'll find patterns in your trash bag. You'll find U-shapes, or you find really wonky functions, and then things have gone wrong. We can also do it. We can also do a check for the residuals, and again, we don't see. So remember those funnel plots that we saw by regression. So we can plot fixed predictors, and then we shouldn't see any type of pattern here. So if we saw a funnel, that means that for some things we're over or underestimating what's going on, but I don't really see a funnel type of thing going on here. So perhaps you differ, but I don't see really any type of funnel in one direction or the other direction. So that's good. So it means across the value of the fixed predictor, we're always making the same type of error, and homogeneity variance is an issue if we have a funnel, because it means we're making more errors along one side of the predictor than opposed to the other side of the predictor. Yeah. Some tips. So centering. So most of the time it makes good sense to center your variables to make them more interpretable. And if you're interested in cross-level interactions, you might recall, so for ANOVA and for some other things, in the exercises that you centered your variables before doing the analysis. And that's to make them interpretable. So especially if you want to test cross-level interactions, so you want to find out if mixed-sex interacts with people's, so mixed-sex classroom interacts with people's intake score, you have a hypothesis about that, you would have to do some centering in order to avoid some making erroneous inferences. So you need to do centering if you're going to do look at cross-level interaction. So basically create a grant mean, and then you subtract everything from that grant mean as you've done in the exercises. You've centered variables before. And that's to avoid that you make problems in inferring what's going on with cross-level interactions. Statistical power, depending on the effect you're looking for, you need to remind yourself that these type of models are data hungry, so you need quite a lot of data. But you can actually simulate by an R package how many cases you would need for your multi-level model to work. And so there's packages which you can do that. So usually before you set out to do your experiments, estimate how many trials you're going to need for a stimulus or how many blocks you're going to need if you're going to run a multi-level model. So there's ways to avoid post hoc that you find, oh, it doesn't converge or we're having lots of issues, to simulate how many cases you would have or how many cases you would need at each level to find the effects you're looking for. So you might have wondered, so today we talked a lot about p-values and AIC-BC, but we didn't have any type of effect size measures. And usually we care about effect size measures as well, like Cohen's D or R, like Pearson correlation coefficients. These are generally not easy to obtain for multi-level models because you have two levels. And so the question is, do you want to look at the top level or the bottom level or the overall model? But there are ways to get them. And so in case you need them, you can look at intra-class correlation coefficient, or you can look at pseudo R squares. You don't have proper R squares, but there are ways to calculate R squares. So if your supervisor says, I don't want to use multi-level models because you can't get R squares, he's wrong because you can get them, but they're just a lot harder to get. So what we haven't done today, and what we might not do in the end, but you will do for your assignment, is we haven't had a case where we have more complex models, where you have classes nested in schools, for example. We've only looked at school level and then the individual level. But if you have a scenario where you have classes in schools, this is what it would look like. Yeah. So this is the type of pattern you would have. So in other cases, also you might have therapists nested in hospitals, nested in neighborhoods or regions. So you might want to have more than one level. And we've only dealt today with very, very simple type of things to get us started with just a school level and an individual level. But in reality, you can have way more levels. So you can also have some relationships which are non-nested. So in this scenario, all the classes are uniquely attributable to a school. They're always part of a school. Yeah, there's no class which exists outside of the school. So all your data is perfectly nested. But you could have a scenario where people are parts of different groups, and you want to account for the fact that they have the same doctor, but also are going to the same school. So in that cases, there might not be perfect overlap because children might be using a different doctor than depending on the school they're going to, or it might be completely independent from one another. So you can't really assign every doctor to the same type of school. So in that case, the scenario would be like this. You would specify two random effects. So this one accounts for the fact that people use the same doctor, and this one accounts for the fact that people use or part of the same school. Yeah. So those are non-overlapping groups, so you can also accommodate for them. If you have a nested scenario, that's what it would look like. In this case, this wouldn't make sense because not every doctor is assignable to every school, and vice versa. You can also do it in LLM Inc, but it's a lot harder, and you can find out for yourself how it works, but it basically involves lists. So you can have ever more levels, and you can tumble through all the misery of creating those type of things. So these are just, I've shown you these graphs before to give you an idea, but we can also bootstrap the effects. So rather than using the p-values, we can bootstrap the effects. It's sort of overflown here, so I'll show you again what it looks like, and then we'll stop. So that was a Stargazer model. So it sort of tailed off here, so you just missed the last bit, which says how many bootstraps. This will take a lot of time to do because what it's doing is it's bootstrapping within each cluster. So it's taking a cluster and then saying resample from this cluster, but keep the structure of the data. So that's really cool. So we can infer the error, so we can infer the uncertainty of our parameter estimates while keeping the same data structure. And so it's the same type of thing. You've done bootstraps before, so it's the same type of setup. We set up a bootstrap. We say the model we want to bootstrap. We say which type of effects we want. You might also want to have the random effects, but here we want to just look at fixed effects. The type of Bootstrap, I knew there's many different types, but here I use a case. So you sample in cases. You might be interested in not sampling cases. You might only be interested in group level effects, in which case you wouldn't use a case thing because you're only interested in the school level effects, for example. Then you would change that. And you would say you do resamples, and this is just some code to say this will correspond to how many levels you have. So if you have 3 levels, you would have 3 truths. If you have 4 levels, you would have 4. So it's basically, you want me to resample from, if we say false, we can say, don't resample from that level, so keep that the same as something else. And that's sort of what it will look like. And then you can, I'll just quickly show you this, and then we'll stop. We can skim it again, but we can also get to 95% confidence interval for our effect. And then you would report out just by saying a case for sampling Bootstrap procedure with 100 resamples show that the effective school average was robust. And if it doesn't include 0, then it will mean it's a robust effect. So that's all I had to cover today. I went a little bit fast, but I'll pick up where I left last time. I'll try and put the dataset online for people who were unable to mount the dataset. And there is an exercise which unfortunately also relies on that package, so I'll also upload the dataset. You can use that. Actually, no, this one doesn't rely on package. You can just download the dataset directly from my website. Okay, that's all I have to cover. Any questions, post them in the discussion boards, and I'll correct some of the issues on the slides, because unfortunately it overflows a lot with lots of long strings of code. Sorry.
Yeah, no problem. You need little spell works. You doing all right? Yeah.